Okay, so today we're going to be shifting to the higher energy side of excited state spectroscopy. So you just finished the optical regime with Frank, and now we're going to move into high energy core X-ray spectroscopy. Before we get to the talk, though, I want to start with one of the most important parts, and that's first by thanking the people who are going to be leading the excited state spectroscopy tutorials this afternoon. So you have quite a team of experts who have extensive experience doing this, both experimentally and computationally, so take advantage of it. They're the people doing the real hard work. The material was largely put together by Tino Rommel, a group leader in my department, and Dimitrios Manganis from Frank's department. So you'll have sort of both ends of the perspective there. And then we have both PhD students, postdocs, as well as other group leaders who are going to be there to support any questions you have during the practical. In addition, today, right after lunch, we have the facility tours. So I hope you guys really enjoy this. I have to say that this campus is a really special place, and I had the privilege of first learning about the Max Planck Institutes roughly about 20 years ago. And I came here and thought, wow, like if I could ever be here, that would be amazing. And now I am here, and I still think it's amazing. And one of the things you'll see is that there's very little that we don't have access to spectroscopically. So it is a real haven for spectroscopists. And what you're going to see today are what are known as the joint workspace laboratories. They're kind of part of this whole construction of the Mülheim Chemistry Campus. And those labs include the Raman, UV-Vis, rapid freeze quench and stop flow instruments. And then you'll also visit in the deep basement our X-ray spectroscopy lab. So I think probably one of the more extensive in-house X-ray spectroscopy setups that you'll see. Okay, but let's just put this first in context. As we talked about earlier this week, the purpose of the school is to basically take this journey through the electromagnetic spectrum and really give you an idea of how all of these spectroscopies relate to each other, how they complement each other. And today we're going to go from the optical, which I think Frank probably convinced all of you, you're going to plot it in wave numbers, right? I wasn't there for his talk, but I suspect this was an issue. We're moving to the X-ray regime now, so my chosen unit is going to be electron volts, simply because there's 8,065 wave numbers to an EV, and it gets a little cumbersome to talk about otherwise. Okay, so that's just your calibration in terms of units. And of course, this is where we sit in the electromagnetic spectrum. So on the very high energy side, you'll see that Mossbauer is actually shown higher. This is just because it's hard to show in a graphic, right? Gamma rays that we use for iron Mossbauer, those are at 14,000 electron volts, or 14 keV, which we'll sometimes say. We only separate them out because they use a gamma or natural source. But in fact, you can also do Mossbauer with synchrotron radiation. And so really X-rays span this whole regime from hundreds to literally tens of thousands of electron volts. And of course, what you have access to depends on the source. And sort of, I think for most of you, at least through your early careers, you probably mainly heard about X-ray spectroscopists going to synchrotrons. And that's in large part because in the last sort of 50 years, that's where the broader application of X-ray spectroscopy really evolved. But keep in mind that the first X-ray spectroscopy happened in laboratories actually as early as the 1920s. And we've sort of seen a revolution in recent years of bringing this back. Why it evolved at synchrotrons, though, is, I think, quite an interesting story. It happened both here in Germany and in the US almost exactly at the same time. And there were particle physicists actually doing collider experiments. And their collision experiments, as they accelerated these particles, either protons or positrons, or electrons, produced radiation at tangents. And so basically, the earliest X-ray spectroscopy was done completely parasitically as a byproduct of high-energy physics research. It was in the 1990s that these facilities became dedicated, and there are many of them. I'm showing the Stanford Synchrotron Radiation Laboratory here, as well as the advanced photon source here on the left. These are both US sources, but there's numerous sources in Europe and around the world. And what these sources do is to produce very intense sources of radiation. And so the units I'm using here are photons per area. So this is really a measure sort of the concentration. So we often talk about these sources having very high brightness or high flux. And so if you compare them to standard laboratory anodes, what you see is that these sources are much more intense. And that's certainly very true for the most modern X-ray free electron lasers, which also give us pulsed time-resolved sources of X-rays in the femtosecond regime. So this is a field that is in many ways really rapidly evolving. These days, according to lightsources.org, there's over 60 large-scale facilities worldwide. I sometimes joke with my group that I use this as a recruiting tool, right? Look at all the places you can go to use large-scale facilities and do X-ray science. But the reality is when they go to these facilities, we're typically working 24-hour shifts around the clock. And suddenly all of these facilities look kind of the same from inside a synchrotron facility. And so with that in mind, I think for all of us, even in the synchrotron world, as much as we enjoy the opportunity to go to beamlines and really use state-of-the-art facilities, there's a lot of more standard X-ray spectroscopy these days that you can do in a laboratory. And I just want to point this out because I think for all of you as you go into your independent careers, I think it becomes more and more realistic that X-ray spectroscopy can become a relatively standard part of your toolkit. And there are companies, both in the US and Europe, that now sell turnkey instruments. One of them you will see today after lunch. It is our Easy XFS instrument that was purchased from a company founded by the University of Washington, Jerry Seidler's group, that now sells instruments to do in-house X-ray absorption and emission. Arguably, this is only for concentrated samples, I would say on the level of 1% weight. So it doesn't work for the enzymes that my group is interested in, but it's actually a great instrument for molecular species or heterogeneous catalysts. And one sees more and more people actually using these kinds of setups in their laboratories. And we've been really fortunate to have a long-standing collaboration with the Berlin Laboratory for Innovative X-ray optics that's actually run by Birgit Kangieser's group. And together in 2014, I got an ERC Consolidator grant that funded our in-house X-ray emission instrument. You'll also at least see this instrument this afternoon. It's affectionately known by our group as Emma, and that's because for those of you who know the German reference to the kid's story, it apparently resembles some locomotive train that's referred to as Emma. I never can remember the full reference. But anyway, you can ask the technical staff who support the instrument because they named her. But that's Emma. And then over here we have Molly. Molly is called Molly because of her molybdenum anode, but she is a source for doing in-house XFS and has multiple ports so that we can even do high temperature and reactor kind of studies with flowing gases. And so that one you'll actually use. And then you won't be able to ignore this instrument, but you won't use it. It's a rather large in-house soft X-ray optical pump, soft X-ray probe that has a nanosecond time scale. So this is a pretty unique instrument. We're still commissioning it and getting it up to where it really needs to be to do more standard experiments, but it just kind of gives you an idea of where the state of the art is in terms of X-ray spectroscopy. And this is really a passion in my group. We have not only our in-house instruments, but we've been actively involved in building up beamlines at synchrotron facilities. This is our beamline at Berlin, which is known as PINK, because it uses pink beam as opposed to monochromatic beam in order to have a more intense source for doing non-resonant X-ray emission. Hopefully, if I don't talk too much, we'll get to that at the end, but one never knows. Otherwise, talk to me about it later. We've also recently built up a second beamline at Bessie and are building up a third one now at Petra. So this is something that my group is really interested in, and in a sense, I hope it helps you appreciate the diversity we need to do science, right? My group absolutely needs great chemists, but we also need great physicists and engineers and also the biologists and biochemists that are producing the enzymes in our group. One of the things, though, you'll see these in the lab tours and practicals this afternoon, but I do want to emphasize, because it's something that that I sort of have to keep in balance as someone who's also a large-scale facility user is that we need the large-scale facilities to keep pushing the forefront of science, but at the same time, state-of-the-art science doesn't necessarily require a state-of-the-art facility. Sometimes we have to uncouple what it is that we need. And I just want to give a shout out to my group and the publications we've had that have been done entirely using in-house instruments and not necessarily needing a synchrotron. Okay, but that's enough advertising for now. I want to get to the heart of this talk and hopefully give you guys a sense for the kinds of things you can get out of X-ray absorption and X-ray emission spectroscopy. So we're going to start by, the majority of this talk will focus on X-ray absorption because I feel like that's the method that is going to be most accessible and most used by the majority of people. And so this is a field that also is rife with acronyms, and people in different fields tend to use different acronyms. But largely speaking, X-ray absorption spectroscopy is referred to as XAS. But you'll also often see X-ray absorption near-edge structure, or XANES, that refers to the XAS edge region. And we'll go through to some of these basic definitions, how the experiment works, what you can get out of it, and how you can analyze it, particularly with regard to DFT-based methods that you'll use in this afternoon's practicals. Then we'll talk about XAFs, which is something that I think is probably pretty familiar to most of you. And then finally, at the end, if we have enough time, we'll talk about X-ray emission methods, or at least briefly introduce it. Okay, so the big strength of X-ray spectroscopy, I would say, especially relative to something like optical or even valence photoemission methods, if any of you are more on the material side, is that we have very high element selectivity. And that element selectivity comes from the fact that we're ionizing core electrons. And so these edges that we're talking about, they result whenever a core electron absorbs an energy that's equal to or greater than its binding energy. And so for copper, that happens at around 9,000 electron volts for a 1s electron. For iron, that happens at around 7,000 electron volts. So these events are separated by 2,000 eV. And it means if I have a complex system, I can very separately look at the copper and look at the iron. And in many spectroscopies, if they're both paramagnetic or if they're both optically active, these are things that overlap. So I would say this is one of the biggest strengths of X-ray spectroscopy is its element selectivity. Now what you see as we move down in energy, the L edges, these refer to ionizations from the 2s and 2p levels. You can see these take about an order of magnitude less energy. So they're around 900 or 700 eV. They fall into what we often refer to as the soft X-ray regime, and you can see their energies are getting closer. And as we go even further out towards the valence to the M edges, these are from the 3s, 3p, and 3d levels, you can see that even copper and iron start to have overlapping energies. And this is also what you see in valence photoemission. This is what we as spectroscopists refer to sometimes as spectral congestion. And it's this idea that you have overlapping features that make unique identification more challenging. Now, my group, we actively use both soft and hard X-rays, and there's various reasons for doing that in terms of core whole lifetime, in terms of experimental setups. For the purpose of this talk, though, I'm going to focus largely on the hard X-ray regime and just sort of allude to different information you would get in the soft X-ray regime. Okay, so with that understood, let's just take a look at standard X-ray absorption data that would be something you might get straight off of the beamline. So what we're monitoring here is the absorption function mu as a function of energy, right? So this would be a typical X-ray absorption edge, and we typically divide it into these two regions, the edge or XANES region, where we largely get electronic and geometric information, and the XAFs, or extended X-ray absorption fine structure region, where we largely get metrical information about what surrounds that photoabsorbing atom. And what we're going to start with is just focusing on what you can get from XANES. But to do that, we just need to look briefly at what this experiment looks like. And you guys just covered optical spectroscopy. And in many ways, X-ray spectroscopy looks pretty much like an optical experiment, with the caveat that we replace our UV-vis light source with an X-ray source. So that could either be my in-house anode or, in most cases, a synchrotron source. And we need to then actually get those X-rays to the energy that we want. So we typically use a double crystal monochromator where the angle at which the X-rays come, using Bragg's law, select for a specific energy. So we're selecting the incident energy using an optic. We then use typically gas-filled ionization chambers to measure the intensity before the sample and to measure the intensity after the sample. So in the simplest experiment, this basically just follows Bragg's law. It's just a simple log of I0 over I1 type measurement. Now, the advantage we have with hard X-rays, and by that I mean greater than 5 keV or greater than 5,000 electron volts, is the X-rays themselves have a relatively long path length in air. And this means that I can always simultaneously measure a reference foil, which is quite helpful in terms of thermal drift or any instabilities. We typically know our reference energy quite well because we're measuring it simultaneously. What you'll see, though, is that my sample here is rotated by 45 degrees, and I have another detector here. And this is in part because the phrase X-ray absorption spectroscopy is a little bit of a misnomer. It's not that often that we measure true transmission absorption. You can do that in a relatively concentrated limit, so 1% weight or higher, that's going to work just fine. For dilute samples, we normally are going to measure a secondary process. And so here it's helpful to talk about what secondary processes are actually happening in my sample. And of course, once I create this core hole, the system can relax in various ways. And a pretty high probability exists that you could actually have an Auger or electron yield decay where you actually eject a photoelectron. This has relatively high probability, especially at low energies, but typically, if you don't have to follow an ejected photoelectron, you don't want to because it has a very short path. And so if there's a strong probability of getting fluorescence, which is true for all of the 3D transition metals, they have relatively high probabilities of fluorescence occurring after the formation of a 1s core hole, then what we like to do is follow the emission. So this would be a 2p refilling the 1s and giving off this fluorescent photon. And so very often, we make the assumption that this fluorescence process is proportional to the absorption. And we'll talk about later how sort of accurate that assumption is. It's an interesting discussion. But this is in general how most people are going to do hard X-ray absorption experiments. They're going to detect in total fluorescence yield. Look at all the fluorescence events that are happening. Okay, this is though, let's just go back one. This is a typical inside of the hutch, right? And so this right here would be a typical fluorescence detector. So I often might have my sample sitting here behind I0. It's in this long tube as a cryostat. This happens to be cooled to helium temperatures in order to minimize damage at my sample. And then here I might have a fluorescence detector. We don't have time to go into the details of how these detectors work, but it's something I'm happy to talk to you about if anyone is interested. And here I just also want to emphasize that this is a setup for hard X-rays. 2 to 5 keV we refer to as tender X-rays. The path in air becomes much shorter, and the beamlines often become encased in either helium environments or in rough vacuums. Less than 2 keV is what we refer to as soft X-rays. Then we need to start using ultra-high vacuum, and that sort of introduces all kinds of other issues. Not that they're insurmountable, but they can be addressed. I want to talk a little bit about what is happening upstream, just briefly, because this is something that you don't often see. Most of the time, if you're a user at a synchrotron, you basically come in and use the experimental hutch. But this is just a reminder that the synchrotron radiation is coming off the ring, and it's typically being amplified by magnets that deflect the beam and intensify what you see. Then we often have slits as well as mirrors that help shape the beam. And so one of the things I want to say about all of these upstream optics is they're taking really high power loads, like many watts of intensity that are coming off the synchrotron. And so it's just interesting to see that they either need to be water-cooled at relatively high flows. This is the water-cooled one. These are water-cooled mirrors. Or they even need to be cooled by liquid nitrogen. And so this is just an example of a monochromator that's being cooled by liquid nitrogen to keep the crystal itself from being instantly distorted. And just to sort of emphasize the power of the X-rays that are being generated by these synchrotron facilities, this is actually a picture from when I was a beamline scientist at SSRL during the commissioning of a beamline. So it wasn't open to users, there were no safety violations, but limits hadn't been set on where you could steer the beam. And so the engineers had actually steered into a piece of copper shielding just for a moment. But this is a rather thick piece of copper shielding that instantly melted with the energy of the beam. Why am I bringing this up? I'm bringing this up because it's something that one needs to be very cognizant of when you work with a source that in itself can do that to a piece of copper metal. Now, by the time it gets to your sample, it's been heavily filtered. And this is why my group and I, we spend a huge amount of time actually trying to figure out how much flux we can put on the sample, what is the dose, how long can we afford to sort of scan at each spot. And photoreduction is a serious issue, especially for biological samples. So we often are monitoring spectral changes as a function of dose, as a function of time on the sample, to see how you actually get a non-damaged sample. This is something the enzyme community cares about a lot. There are other communities that kind of ignore this. And for me, for any of you who venture into X-ray spectroscopy, please keep this in mind. If you're putting 3 watts of power into a sample, I don't really care what it is. Like, it can melt copper metal. So just think about it in your experiment, what power density you're putting on. The upside is that if your sample is stable, you can measure it in almost any form. And this is the nice thing about X-rays. We can measure solids, liquids, gases, frozen solutions, flowing solutions. We're quite flexible with our sample environments, especially for hard X-rays, because we can design basically any sample environment that the X-rays can penetrate. In terms of concentration, it's hard to give you a definitive answer. It really depends on the beamline itself, so how much flux it has, what the beam spot is, how much volume you need. But we typically say you need about a 1 millimolar concentration in the photoabsorber. So that's like 1 millimolar iron if you want to measure the iron K edge. It will vary, though, a lot by element. So as you get to heavier elements, like selenium, for instance, the records there have actually been to push down into the nanomolar range. And that is not work from our group, but from Graham George's group in Canada. But it is possible to go to lower concentrations. That said, they become incredibly heroic experiments with limited beam time. So most of the time, if you can go concentrated because you'll get data faster. If you have a heroic reason you need it, then one can think about how to design that experiment. We can work with relatively small volumes on certain beamlines. So I think, again, sort of there are setups that deliver droplets, and one can start to think about microliter volumes with focused beams. But standard is more like 100 microliters for our typical samples. Okay, so let's say we actually have our experimental setup. What kind of information are we actually going to get out of these X-ray absorption edges? And so I already sort of roughly divided it into the edge and the x-axis region, but what I want to focus on right now are the pre-edges, which are these very weak 1s to 3d features. These are formally a delta L of 2, right, S to D. So they're dipole forbidden, but they're quadrupole allowed. And then the edge is formally, in this case, the iron 1s to 4p. So it's a delta L of 1 going from S to P. It's dipole allowed, and that's what gives us this intense edge. And we're going to focus on just sort of how these edges change as a function of oxidation state, coordination number, covalency, and site geometry, or 4p mixing. And so what I want to do is just give you examples that illustrate how each of these changes manifest in the edge. Okay, so let's start with how metal K edges are affected by oxidation state. And so what I'm showing here on the left at just below 9,000 electron volts are copper K edges of a copper 1 in blue and a copper 2 in red. And so what you can clearly see is that when we're more oxidized, it takes more energy because we have a higher effective nuclear charge to actually ionize the 1s electron, and the edge shifts up. So that's a simple metric that these edges reflect something about oxidation state. But what I'm comparing here also are different iron 2 and 3 comparisons. And so these are iron tetrathiolate complexes where we have a ferrous or iron 2 form and a ferric or iron 3 form. And you see the edges shift up, not quite as much as they did at copper, but they do shift up in energy with oxidation state. And something similar happens when I compare Fer-O and Fe cyanide. There's also a similar shift in the edge. But what you can see is the overall shape of these iron edges is entirely different, right? If I have 4 sulfurs versus 6 cyanides, they look nothing alike. And this is one of the things I just want to emphasize is when you want to use edges as oxidation state fingerprints, you need to be comparing related things, right? Otherwise, it really doesn't make any sense. But when you actually do have related comparisons, these edges actually contain a lot more quantitative information. So for instance, these edges also contain information about coordination number. Probably one of the clearest examples is in copper 1, and so that's why I'm using this as an illustration, but there are other examples where we can extract coordination number from the edge. But here I'm just starting with an illustrative example of what happens going from 2-coordinate to 3-coordinate to 4-coordinate copper 1. And you can see the 2-coordinate has this very intense transition in the rising edge. And so it's useful to go back to these simple considerations that we already talked about in our ligand field lecture to talk about what these features might be in an intuitive sense. And so we can start with copper, just a naked copper 1 ion, where the 4p xyz orbitals would be degenerate. Now imagine that I bring in 2 ligands along the pz axis. Due to antibonding interactions, I'm going to raise the energy of the pz, and it's going to become antibonding, and I'm going to have a low energy xy that's doubly degenerate. And so the intense transition we see here is actually to a doubly degenerate pxy in a sort of simple picture. But actually, nicely, you can also even show this these days with ORCA TD-DFT calculations, nicely reproduce this. Now, if we go to a 3-coordinate complex where I have 3 ligands within the YZ plane, then both Y and Z will be raised due to those antibonding interactions, and I predict that I should have a single PX transition with roughly half the intensity of the 2-coordinate that had a doubly degenerate PXY, and that's also what I see. Then when I go to a 4-coordinate copper 1 that's tetrahedral, I'm going to raise the energy of the P, X, Y, and Z symmetrically relative to either the 2 or the 3-coordinate complexes such that I expect the degenerate XYZ to largely be buried in an edge transition. And that's also roughly what we see in the red spectrum. And so this is just to give you the idea that these edges can convey, in many cases, relatively intuitive information. Now, this isn't always the case. Nothing is easier than dealing with D10. That's also the beauty, though, of X-ray spectroscopy, right? D10 systems like copper 1 and zinc that you don't see by other spectroscopy, we still see. And we can also interpret them pretty rigorously because we don't have any secondary processes happening. When we get to something like copper 2, though, you can already see that the situation gets a bit more complex. And so this is actually very old work from my own thesis, so 25 plus years old by now. But what you see is these are 3 related copper 2 edges where the onset of the rising edge actually changes. And I won't go through this in detail other than to say the nature of just one ligand was changing. And the way we interpreted this was that this was a so-called shakedown feature. And this is similar to ligand to metal charge transfer or shakedown transitions that you might see in photoemission spectroscopy. It's just the idea that after this initial metal 1s to 4p transition, it can be possible that due to the increased effective nuclear charge that results from this core hole, that this 3d can actually relax below the level of 3p, making an LMCT event favorable. And so in a state-based picture, the way I would see this is that I have a 3d9 ground state that is lowest in energy in the ground state, and a 3d10 ligand hole state. This is my LMCT state. And in the presence of the core hole, this ordering can actually change, and that gives rise to these so-called shakedown features. And so this is just something to keep in mind, that there are other features that can be superimposed on the rising edge that can be highly diagnostic also of the nature of the ligand. In fact, the nature of the ligand is so diagnostic in X-ray absorption edges that it can shift the edges dramatically. This is an example of iron 3 with either fluoride, chloride, or bromide. And what is quite interesting is that the pre-edges are relatively similar in energy. But what varies actually dramatically is the rising edge position, where the heavier scattering bromide appears at much lower energy than the light fluorine. And this is interesting to think about, to what extent this is shakedown, to what extent this is differences in scattering property, or maybe some combination of both, right? But we know these are all iron 3. From Mossbauer, they're certainly all iron 3. But interestingly, this part of the edge, although it works fine for copper 1, in open shell metal ions, simple DFT approaches certainly break down. Scattering-based theories don't get the energetic trends correct either. So this is a little bit of a no man's land in theory, and something that we still need to address, although experimentally incredibly rich. So another argument of why we need to advance our understanding of that spectral region. That said, the pre-edges, which tend to be intrinsically weak because in a centrosymmetric limit they are only quadrupole allowed, these are incredibly informative. And so we talked about in the group theory talk that I was going to use octahedral and tetrahedral examples a lot. The reason that I'm using this is, of course, in the octahedral limit, what one sees if we were going to go to our OH group theory character table, we would go back to seeing what we already saw on Monday, that our d orbitals transform as T2, G, and EG, but our 4p orbitals transform as T1U. And so there's no mechanism to get any p character into this pre-edge. Hence, this pre-edge is weak, and it reflects only a pure 1s to 3d quadrupole transition in rigorously octahedral symmetry. But what you nicely see experimentally when we go to a tetrahedral ferric tetrachloride complex, from group theory, we see that, of course, the 4p orbitals now transform as T2, and we also have a triply degenerate set of T2d orbitals that transform as XY, XZ, and YZ. And so this gives you a means, by group theory, for P and D to mix. It gives you a mechanism to get dipole allowed character, which will give you much more intensity, about 100 times more intensity than quadrupole. So you only need a small amount of 4P to get this, and it's immediately reporting on large differences in site symmetry. Okay? And you can actually assign this much more rigorously from single crystal experiments. I'm bringing this up just because it's something I particularly enjoy, but not that I expect many people will want to do this. But these are old single crystal experiments we did just to really rigorously show how these pre-edges can be assigned. And so at the time, computationally, we had sort of said from a group theory considerations, I'm in C4V symmetry. I should have an intense mixing that occurs in the Z direction, where the PZ and DZ squared can mix, because I have a very short manganese oxo bond, right? This would be covalently mediated. And to actually test this hypothesis, we actually looked at what happened, and we showed that when you had your X-rays along the manganese oxo bond, you had maximum intensity. And as we rotated our crystal off the manganese oxygen bond until the point we were perpendicular to it, we had minimum intensity. And when we actually do this rotation in the plane, we only see mixing into the E set, the XZ, YZ, that are more modestly modulated. But this is just a nice way to see how that actually contributes to these pre-edge intensities. We also had polarized single crystal XFs that allowed us to separate out the axial and equatorial vectors, an experiment that one can do, but not easily. So good. So let's look then at some of the general trends that we can talk about in terms of pre-edges. And again, this all comes out of group theory. And one of the sort of early observations that was made initially by Larry Kay and then in excruciating detail by Ed Solomon's group in the late 90s was this idea that 6-coordinate complexes should have weaker pre-edges than 5-coordinate complexes. And that is a completely group theory argument. It assumes that your 6-coordinate complex is octahedral, and of course your 5-coordinate complex can't be. It has a mechanism to gain intensity. The other sort of standard metric that's often in the literature is that pre-edges shift by 1 unit 1 EV per unit change in oxidation state. So this is an example of iron 4, 5, and 6, published some time ago with Carl Wietkart's group and John Barry, who's now at Wisconsin, who was a postdoc at the time. And this is just a very nice series. I should point out that very recently with Karsten Meyer's group, we also have identified an iron 7 that actually still basically continues to fall on this line. So these are kind of unique and very cool examples. But one thing I want you to always be aware of is there's an exception to every rule, right? And we always have to be careful. This sounds like a good rule to find out coordination number or to find out oxidation state, but let me just show you some clear exceptions to this. This is a complex where we have a small molecule crystal structure. We absolutely know that it's 6 coordinate. But if we just use the pre-edge intensity or area of this red line, we might assign it as 5 coordinate. But when we look at the crystal structure, we can easily understand that while it's 6 coordinate, it is rotated from octahedral, right? And so once we have distortions, we have other mechanisms for intensity. And this is exactly the reason why we want to use as many spectroscopic methods as possible. And just to maybe point out, I see some of you squinting at these edges. We generally have to fit a background and then integrate the area. So that's how we're typically comparing these areas. Let's look at the other sort of exception to the rule, and that is this idea that these pre-edges have to shift by 1 EV per unit change in oxidation state. These are complexes that by Mossbauer that we assigned as iron 4 and 5 complexes, but you actually see that from the pre-edge they're nearly identical energies. The reason the iron 5 in this case, the black one here, is not actually to higher energy is because it's actually 5 coordinate. And so the ligand field locally actually decreases and the 3D manifold drops down. What you do, though, beautifully see is that because it's 5 coordinate, it actually has a mechanism to gain intensity in its local C4V geometry. And so we kind of have to take all of these factors into consideration when we make these types of assignments. And so at some point, I don't even know how many years ago now, maybe it's coming up on 20 years ago probably, that Frank and I discussed the extent to which you could actually directly calculate these spectra. And so if you look at the papers that sort of predate this, there was a lot of handwork done with programs like ADF that I myself kind of also did during my grad school years, where you had a giant Excel sheet and your ADF calculation, and then you tried to like hand make a spectra out of sticks. Not recommended, by the way. It took a long time and it was silly. But we, as you'll see, and you'll do this afternoon, these are calculations we can do in ORCA super fast, like on your laptop, takes no time. It's just astounding, right? And what you can see is that these pre-edges that we talked about, going from the octahedral to the tetrahedral limit, not only do you beautifully get the trends in ORCA, but you can also really break down the quadrupole and dipole contributions and nicely see, as we discussed, that in octahedral ferric tetrachloride, that is a quadrupole only contribution, where the dipole here is a flat line. And this all comes straight out of the calculations you guys will be doing this afternoon. Now, one of the things that I'm not highlighting is that typically to make these kinds of correlations, because we don't want to just calculate and say, oh, look, ORCA can calculate my spectra. What we want to do is to use it in a predictive way and to say, hey, I have an unknown, and based on a series of knowns, based on the calculated energies and areas, can I predict what models are consistent with my data? And so what we like to do is to actually come up with these sort of calibration plots where we have experimental energies relative to calculated energies and experimental areas relative to our calculated sum of oscillator strings. And so what we see, these are old numbers now, where we were within about plus or minus 0.3 EV. From some of the ORCA team developments, this is getting closer to plus or minus 0.1 EV. And with areas, we've actually generally been actually quite good in terms of the correlations. One thing, though, I'm not telling you about is that I'm focusing on the plus or minus. And what we care about is getting the trends right. So we have to establish scaling factors. At a given level of theory, I need to shift by, in one method, by 183 EV. If I add relativistics, the shifts become smaller. But my point is, I only care what the plus minus is. I don't care what the absolute energy is. And the reason I say this is because as much as an experiment is forever, you also have to be honest with what we as experimentalists actually know. how accurately do we actually know our energies? And the reality is that we all calibrate. We have different reference books that we pull out. And if you look even in the US, I picked 2 synchrotrons. The iron in SSRL on the west coast of the United States is 7111.2 eV. But if you go over to Brookhaven Lab, it's moved by 0.8 eV. And it's not that iron has shifted, right? The foil is the foil, but simply that people have historically used different references. And it gets even worse for other metals. You can see here the differences in copper. Sulfur, even at low energy, these shifts are more than 2 electron volts, right? And so again, so much of this is historical. And so when theoreticians tell me they want to really accurately get the energies, one has to ask, do the experimentalists actually accurately know them? And this is why we have to thank people at the NIST and the PTB who are pushing the forefront of actually getting these numbers right, but don't pretend that we as X-ray spectroscopists know these numbers for many of the things that we're measuring in an absolute sense, okay? Good. So let's talk about how we can use this in a predictive way. And one of the things I just want to point out is these are a series of high-valent iron oxos, and the experimental data are above, the theory is below, and what you can see is we get the general trends pretty well. And these are all done with just simple TD-DFT. And that, of course, goes against everything that Frank and I have been telling you in our previous talks, right? Because TD-DFT effectively is in a sort of cone sham-like orbital-based picture, right? And one could ask then, why is this working so well? And one of the reasons it works so well, especially in high-energy core X-ray spectroscopy, I think, is because our resolution is so poor. You can look at these pre-edges, they're relatively featureless. We actually have an intrinsic core hole lifetime broadening that is larger than an electron volt. And so in effect, our data and the core hole lifetime broadening is masking probably a lot of those multiplet effects. There are some multiplet effects, though, that TD-DFT can capture. And this is really through spin polarization that we can kind of get what we refer to as poor man's multiplets. And I'll show you a bit what that looks like, how spin polarization manifests in these calculations. But the other aspect is that PD mixing means that dipole character can actually mask the multiplet structure. And so if you think about the fact that, for instance, in this OXO, I have strong PZ DZ squared mixing. So suddenly I'm dominated by really one state, and the other multiplets are kind of masked in the noise. And so that's why I think this tends to work well. And even if it's not the highest level of theory, you can still get insights into your data, and relatively easily, right? We don't always need the most sophisticated calculation to understand our data. And here's a nice example of just how this works and how spin polarization actually gets this correct. If we look at iron 4 oxo, I'm showing here now just the 1s and the C4V splitting of the d orbitals with a ground state triplet versus a ground state quintet. And what you see in the triplet case is that if I think about this being dominated by the DZ squared, I could put either an alpha or a beta electron in the DZ squared. And so these transitions I calculate in TD-DFT, the alpha and beta DZ squared, these are locally quartet and doublet states that are actually just split in energy due to spin polarization. And for a triplet system, the extent of spin polarization is smaller than it is in a quintet system, where instead I reach locally quartet and, sextet and quartet states, sorry. So yeah, these would be my local sextet and quartet states. And this was kind of a fun example. I realize I don't have the original reference in here, but this was actually a prediction that we made using ORCA together with Frank and John Barry before the first S=2 iron 4 oxo complex was synthesized. And then when we got the data, it really had this broadened pre-edge that's kind of become a signature for those complexes. And so that was kind of a fun example that the poor man's multiplets worked, and actually Frank didn't expect them to, I think. He always calls this criminally simple approach, but you know, it always has to just be tested against experiment. Okay. We're at about the halfway point. I don't know, do you guys need a stretch break or do we just keep going? Plow on through. Okay, cool. So we're going to get to the EXAFS part next. How many of you have already had EXAFS in like previous lectures? Okay, not that many. I would have thought more. Okay, we'll see how quickly I can get through this and if we can cover some of the omission at the end. But EXAFS, I think, is probably the most used part of hard X-ray spectroscopy, right? This is kind of what you'll see in the most papers. And not that you guys need to know my personal pet peeves, but there's so much information in the edge that people tend to ignore. And EXAFS, I think, tends to be a bit more of a black box kind of approach where people use it in a very routine way. And they could get a lot more out of their EXAFS if they coupled it from the edge. And I do want to at least focus on that a bit. But EXAFS itself is a scattering-based approach, right? So when we were talking about the edge, it's a picture that we can largely think about in concepts, that we talked about with molecular orbital theory. But now with the EXAFS, our photoelectron wave vector has been ejected to the continuum, and it's now a photoelectron wave that's propagating out, and it's going to get scattered by the electron density of surrounding atoms. And when that happens, the returning wave can be interfering with the outgoing wave either in a constructive or a destructive manner. And that's what gives these sort of wiggles that we know as EXAFS and that we use to report on local metrical structure. And of course, it's not just the photoabsorber and the nearest neighbor, but the scattering can happen off more distant neighbors, and that's what we refer to as multiple scattering. Right? So there are many, many events that are happening, and we're trying to deconvolute all of that to get structural information out. And so one thing that EXAFS is quite good at is getting distances on the order of about 0.01 to 0.02 angstroms. It's not very good at coordination numbers, and this has to do with the fact that there are many correlated parameters in terms of disorder parameters, amplitude reduction factors, that all correlate with coordination number. And this is a place where you could see, hey, my edge could help me. If I thought about my pre-edge, I could reduce that error, perhaps. It tells you about types of ligands within Z plus or minus 1. This means, as with almost any scattering method, carbon, nitrogen, oxygen, they all kind of look the same. And so you need other input to distinguish those. One of those is valence to core X-ray emission that my group has been quite interested in. You can also get some nearest neighbor information. This will depend on the quality of your EXAFS, but I would say a maximum is a distance of 6 angstroms or so from the photoabsorber. And in certain cases, like well-ordered cases, you can get bond angle information. But standard EXAFS sees the average of all photoabsorbers. So if you have a mixture, you see the average of a mixture. And that can be one of the challenges that you can sometimes get around with certain high-resolution X-ray spectroscopy methods, but certainly not in standard EXAFS. Okay, so what does the data look like off the beam? Because obviously, when you're just collecting X-ray absorption spectroscopy, you don't initially see anything that looks like EXAFS. So what we do is we've already measured our raw data in energy space. We typically subtract a background that has to do with any sort of lower energy absorption or scattering events that we remove. And then the next thing we do is to spline our data. And here we're actually trying to remove the atomic background from the absorption curve of interest. And so the spline, in effect, is basically trying to model very low frequency events that would have to do with scattering off the atom's own interatomic potential. So in physics, there's a separate field of people doing atomic EXAFS in the gas phase. But when you're trying to get coordination chemistry information, that's a nuisance, and we're just trying to remove it and somehow model it. These days, most programs have algorithms that just minimize the low R component, and you don't have to think about that too much. In any case, though, this still doesn't look like the EXAFS you see. You can see how weak these oscillations are. But normally in a publication, what you'll see is something in K space, which is reciprocal angstrom space, that I arrive at by converting from energy space, and we'll go through exactly how you do that. And the EXAFS is typically K cubed weighted. And then what we do is we take K space, transform it into R space in angstroms, and we get this sort of Fourier transform where these features indicate the radial distance relative to the photoabsorber at 0. One thing I want to emphasize is that these tell you there's something around 2 angstroms and there's something around 3 angstroms, but please, please, please never read a distance off a Fourier transform. You can't do that. They need to be phase shift corrected, and the phase shift correction is different for every scatterer. So you can really end up in a bad space. Also, we're only showing the magnitude here and not both the real and imaginary components. So again, just simply reading distances is misleading, and XFs really have to be fit. Okay, but once we actually do this subtraction, so this is just to show you that we're basically modeling, we have the measured mu naught, or mu of E, we subtract our spline, which is mu naught of E, and then normally at the E0 point, we divide by an edge jump. And we do this because in X-ray absorption measurements, it's very hard for us to measure a true extinction coefficient like you would in optical. And so it's much easier for us to just normalize everything to 1 unit photoabsorber. And so that's normally what we do. And let me see, what else did I want to tell you about this? This E0 point. This is kind of an important one. This is the origin of the photoelectron wave vector. And so this is actually the point at which we say the electron has been ejected to the continuum. And we're going to use this point to define actually our K space, which I thought I had the equation for, but it will be on the next slide, sorry. So first we do that subtraction, and then we have basically something that starts to look like XFs, but it's all compressed because this is XFs that I've kept still in energy space. And then in the next step, I convert energy space to K space. So here's the equation for that. You can see I have to define E0, and this is a problem because I don't actually know where E0 is, right? It's somewhere around the edge-ish, but to say exactly when something's been excited to the continuum, I can't a priori know. So we normally fit E0 as well, and then eventually we get something out that looks a little bit more like the XFs that you see. And then in the next step, what we have to do is to actually fit this, right? And so to fit this, we need a scattering-based equation that actually describes the XFs, right? And so let's just go through this briefly. This is the actual XFs equation. So we start by basically having an exponential that describes the outgoing photoelectron wave, and also an exponential that describes the returning photoelectron wave. And then what needs to happen is it's going to be modulated by both the amplitude, the f of k parameters, and the phase, the delta k parameters of the photoabsorber. And these parameters will depend on the nature of the neighboring atoms. And so this isn't the form you normally see the XFs equation in, because normally what people have done is they've already done an expansion of this, and they've taken the square of that exponential, and using Euler's theorem, they've converted it to an expression as a sine wave, right? And so this is why it sort of at least intuitively then relates to the oscillations that we see. And so this is just the XFs equation for one atomic site, but you can see that it's dependent on n, the coordination number. It's dependent on r, the distance of the photoabsorber to its nearest neighbor, and it's also dependent on the phase. And I'm going to break this down also visually, how each of these things sort of impact it. But the other important component we have in XFs is the disorder term, or what we often refer to as the Debye-Waller. That's represented as sigma squared, and it's a mean square disorder in R. So this is sort of the analogy of sort of B factors in crystallography. And so this is what we're doing is, this is just another summary of this equation, but we've basically already defined all of these functions. And so what I want to do instead is just give you calculations to show you how this breaks down in real life, because it's kind of easier, I think, to have intuition if you can look at what these spectra look like and how they're modulated as a function of distance. And so here I'm just showing you PHEF calculated. So PHEF is kind of the go-to program in the XFs community. You'll hear about a lot of different programs like Larch and Artemis, but most of them actually interface to PHEF underneath. So PHEF is kind of the internationally probably most used XFs code. And with that code, I just calculated iron-oxygen scattering paths at 2 angstroms, 3 angstroms, and 4 angstroms. And what you can very nicely see is how the frequency changes. So the longer the distance, the higher the frequency. And so the frequency beat of your XFs kind of immediately tells you something about how far the scatterers are away. But if you don't visualize well in frequency space, you can also see it in R space, where we go from 2 to 3 to 4 angstroms, and you nicely see this 1 over R squared dependence. That's what makes XFs a local technique, right? So the longer the distance, the weaker the XFs will be. And probably the easiest effect to see is coordination number. This was the linear n term at the front of our equation, so everything just goes up linearly in the XFs and in the Fourier transform as expected. The very important part of XFs, of course, is that the identity of the backscatter actually matters. And so these are all iron scatterers, to the iron at a distance of 2.5 angstroms. And what you can see is that oxygen is a very light scatterer, so it has a weak amplitude, and it's weak in the Fourier transform. Whereas sulfur is a heavier scatterer, it's going to contribute more, and iron is the heaviest. And when we talk about these sort of amplitude envelopes, what I'm also talking about is the fact that the heavier the atom, the higher in K space it will peak. And so there's actually an amplitude modulation that has to do with the effective charge on the atom. And so the way to think about these modulations even more grossly visually is just that the carbon actually can't have a very strong modulation on an iron photoabsorber. And so that's why these are relatively weak waves, whereas things like metal-metal vectors, they stand out in XFs. Those will be very strong modulations, and they're very hard to miss. The last one I want to point out, and it's an important one, is the effect of DeBeer. This is this disorder term. This accounts for thermal vibrations, but it also accounts for static disorder. Most of the time in our group, we try to do XFs measurements at low temperature to sort of minimize the thermal contributions. That'll generally give you nicer data. But if you're doing an in situ experiment, you can't do it at 10 Kelvin, so you have to, sort of model the thermal and the static parameters into your XFs. And I'm going to talk more about static disorder later, so I'll leave that out for now. But basically, the bigger the number of the DeBeer, the greater the static disorder. So if I have more disorder, the intrinsic intensity goes down. And now you can kind of see why coordination number is so uncertain, because maybe it's disorder, maybe it's a change in coordination number. I don't know. And my tip is look at your pre-edge. Maybe it helps you. So that's just a reminder. Okay, but let's just talk a little bit more about DeBeer here. Here I'm just showing you what happens as we go from 10K to room temperature on the same sample. And so you can really see that as we raise up to room temperature, the red spectrum is significantly damped. And so if I really care about getting a good structural information and good long-range order, I want to do XFs at low temperature if I can. The other thing that you can see is I can get XFs much further out in K space when I'm at lower temperature. And so then the question is, why do I care about this high K data? And that's because the further I go out in K space, the higher the resolution of my experiment. And so roughly speaking, the resolution of an XFs experiment goes as pi over 2 delta K. And that means if I want to separate two similar scatterers that are only 0.1 angstroms apart, I need data out to roughly K of 20. That's fairly rare to get. So most of the time we talk about similar scatterers within 0.15, 0.18 angstroms needing to be grouped together and increasing my static disorder. Okay, so that is an intrinsic problem. But I just want to give you a sense of what it looks like to have very high K data. So I've taken this beautiful data. This is a sample made in Kit Cummins' lab at MIT, and the data were collected by Graham George at SSRL. These are record high K data going out to K of 21. Largely because you have this linear molybdenum, nitrogen, nitrogen, molybdenum vector that gives you a beautiful forward scattering effect. And when I look at how this modulates the XFs, you can see as I go further and further out in K, I start to sharpen up the Fourier transform and I start to see features that weren't there. We'll just go back one more time if it was fast. Need to slow it down, but you can just see how the structure emerges. And so this is why XFs an XAS spectroscopist spends so much time trying to get data to emerge from the noise, because that's where their resolution is actually going to come from. Okay, good. So let's touch a little bit on this static disorder and the Debye-Waller. So, when we teach, we often teach with these rigorously idealized structures like the octahedral site that we can have a character table and so on for. And in a case like this, you're probably going to have all of these iron-chlorine vectors having basically the same exact distance. And at 2 angstroms, you're going to probably have a small Debye-Waller where it's going to be something like 0.003 angstroms is sort of a reasonable guess for that. So 0.001, 0.003, these are relatively well-ordered systems. But for enzyme active sites or catalytic active sites or basically anything that's a real system, you can see, like, I have these complex active sites that have different types of oxygen, different types of nitrogen, but I can't even separate those, right? So it all has to get grouped into some average radial distance that in and of itself will also have disorder. On top of that, I also have all of the multiple scattering that can happen. So if I just imagine that I had a histidine ring, there are all these different pathways that my photoelectron can scatter, and every single one of those gives me a different type of scattering pattern. I mean, this is why XFs in general, we have a real underdetermined problem, right? We have so many possible paths that we can't possibly fit. And so, for instance, if I take the same iron complex that I showed you the XFs for at the start, this is from Torsten Glaser's group, this iron-oxygen-iron complex, and I just put it into Pfeff, it says there are 98 paths that have at least a 5% contribution. And I don't have 98 free parameters that I actually can fit, right? So normally this is our expression for the number of independent parameters. It goes as 2 delta K delta R over pi. So most of the time we're dealing with a number of free parameters that's closer to maybe 10 to 15, but certainly not hundreds, which is what I would need for these 98 paths. And so what we intrinsically do when we calculate XFs is to start grouping paths that are related to each other. And when we do that, we have the problem that we start to have a static disorder component that becomes significant. So as I already pointed out, this Debye-Waller, it has a thermal component, T, and a static disorder component, SD. And what actually happens then is as I have a distribution of distances, I need to know how far those distances are displaced from the mean. And so this is just an example where I have a range of iron distances and I don't have the resolution to separate all of them out because I have too short of a K range. Then I basically end up with all of them grouped at an average distance and with a large static disorder term. So the static disorder term I'm calculating here is around 0.0073. I don't want to go through this in detail, but just to point out that this is something that can really put uncertainty in the Debye-Waller terms. And basically, this is kind of why, just to bring this point home, is if I vary the Debye-Waller and vary the coordination number, as the Debye-Waller actually gets smaller than the coordination number, you can kind of basically just see that it's just an underdetermined problem because these two things are fully correlated with each other. And one of the questions we sort of had going into all of this is, to what extent is XFs predictive? And here what I want to point out is that we can do a pretty good job of fitting XFs, right? This is a small molecule where we have a crystal structure. We put the parameters into Pfeff. We group them as I showed you on the previous slide. We fit them against our data, and the red line is the fit. It looks reasonable. But we can also just take direct Pfeff calculated parameters, either at the crystal structure, which is in blue. That looks a bit off from the experimental data. I can geometry optimize in ORCA and then use Pfeff to do correlated Debye calculations. That's red. That actually looks quite good. But if I geometry optimize and do a more sophisticated treatment of the Debye-Waller using a dynamical matrix method and a DFT-based Hessian, it actually gets worse, which is interesting. But as soon as we get to more complex systems like dimers, again, I can fit it, but then all of my Pfeff calculations, none of them match at longer range. And here I just want to point out that it remains the case that these scattering-based methods are still not fully predictive. They can't actually predict the damping at long distances. And so we used this some time ago to show that in systems like the oxygen evolving complex of photosystem 2, you can't take a crystal structure and directly predict the excess. That is still not possible. And this was about 10 years ago that we actually showed this, but importantly, John Rear, who is the author of the PHEF code, was also part of this study because we frankly wanted to know that we were using his code correctly and that they had really signed off on this. And John is an absolutely brilliant, wonderful physicist who has largely dedicated most of his life to EXAFs of various metal foils. And at the end of this collaboration, his conclusion was, these molecules, they're complicated. So that was at least, understanding and appreciation of chemists. But it remains the case that to this day, EXAFs still have to be fit. I keep telling Frank, like, we should figure out some way to have this in ORCA, but this is, yet another, we'll just leave it at that. So for now, we're stuck with fitting, and if we're going to fit, or if I ever review anyone's paper here who fits EXAFs, I'm just going to give you my sort of laundry list of sort of complaints that things I don't want to see. So with EXAFs fitting, please know the limits of your data. So both the resolution of your data, a lot of people seem to ignore that, and the number of free parameters. So we've given you both of those equations. We really don't want to overfit. There's sort of a limit of overfitting that we don't want to see. The other thing is this: please don't have a different E0 for every path in your fit. This is something that you see frequently, that people define the origin of the photoelectron wave vector, allow it to refine, and then it's moving by 40 eV for different paths. These things become non-physical. And because people put EXAFs fits in the SI and nobody looks at them, right, then sometimes EXAFs gets a bad rap, and it's not fair. It has something to do with the driver, right? And this is also one of those things that one has to be aware of. Do constrain your EXAFs fit based on knowledge from the edge or knowledge from other spectroscopy, right? This is this whole holistic view that we're trying to discuss, that it's so important to actually put these constraints on it. And don't force your XRD model onto the EXAFs. There are some real overfitting examples where people try to say they have the freedom to separate out octahedral and tetrahedral sites. You can do that at the edge. They behave differently. But in a scattering-based picture, if you don't have the resolution, you don't have the resolution. And again, this is where maybe more sophisticated emission methods come in to separate that out. And so that's what we're going to switch gears to. So I already alluded to that in X-ray absorption, we rarely do a true absorption experiment. And that most of the time, what we're really measuring is the total fluorescence or partial fluorescence yield. So we're looking at what happens when the system relaxes back down and a fluorescent photon is produced. And so in a standard experiment, this is the same diagram basically that I showed you before. We generally have our sample rotated 45 degrees, and we're using a solid state detector to measure the fluorescence. Now, what is that solid state detector actually seeing? It's basically measuring the energy of deposited photons, but at relatively low resolution. And this is hand-drawn, so I apologize if it doesn't look real. It's not real. But what you would see on the sort of detector itself are scattering-based features. So we have both elastic and inelastic features. And for something like iron, these detectors will typically have a resolution of about 175 electron volts. So you sort of see big blobs that correspond to a 2p to 1s de-excitation. So that 1s core hole being filled by a nearby 2p electron. Those happen at about 6.4 keV for iron. And then about an order of magnitude lower in probability is the 3p to 1s. But what you can see is that it's relatively featureless. And in fact, in many detectors, as they age, even the K-alpha and K-beta are kind of overlapping. So you just kind of set a window near the iron and hope to hit it, right? And there's been increasing interest in the last, I would say, 15 years or so to have high energy resolution X-ray emission setups that increase the intrinsic resolution by using a Bragg optic. So in a sense, we're doing the same thing that we're doing with our upstream monochromator. But now instead of sending the fluorescent signal from our sample to our low resolution detector, we first send it to a Bragg optic to spectrally analyze that fluorescence, and then we send it to our detector. And so by doing this, we can actually get much higher resolution, and I'll show you a little bit later exactly how that works. But let's just talk about why we would do this first and the kinds of information we get out. So as we already said, we can eject a 1s electron to the continuum. The 2p falls down and produces a fluorescent photon. This is what we refer to as the K-alpha line. If we have enough resolution in our spectrometer, we have K-alpha 1 and K-alpha 2 lines. Those are basically split by the 2p spin orbit in the final state, so into 2p 3 halves and 2p 1 halves. This is actually something that chemically isn't that informative. It largely is dominated by spin orbit, but I will show you a bit later how this enables higher resolution experiments. The other thing we can do is look at a 3p electron, refill the 1s core hole. This is an order of magnitude less likely, but because we've created a 3p core hole, which is energetically closer to the 3d levels, these are final state spectra that are dominated by 3p 3d exchange. That means if I have a lot of unpaired electrons in my d manifold, the spectral shape reports on the number of unpaired electrons. And it has also been used to enable oxidation state and spin-dependent X-ray absorption, as well as XFs. Sophisticated and challenging experiments, but possible in certain cases. And then finally, at very, very low intensity, I've boxed it in here so you can actually see it, are these valence to core transitions. And this corresponds to the very low probability that an electron in a ligand-based valence orbital refills the core hole on the metal. And this is highly sensitive to ligand environment, and it's a good measure of ligand identity, as well as ionization potential and protonation states. And this can also enable some exotic experiments that I will briefly touch on. Okay, but let's just look at the setup in a little bit more detail. I've kind of drawn this out so you can just see a different perspective on it, and so you can see the geometry. Because when we align these spectrometers at a beamline, we're actually sort of thinking of a sphere of intersecting what we call Rowland circles. And so we basically have fluorescence from our sample, and then we have our analyzer crystal. And that analyzer crystal is bent to have a radius of curvature that defines basically the circle that I'm working on. And then geometrically on that circle, I need to also place my detector. And then this will have an angular relationship, which will actually define the energy of detection at the crystal. So again, I'm just using Bragg's law, but because I have ideal crystals, I can go from having a resolution of 175 eV at iron to a resolution of 1 eV. And then these become much richer, much more informative spectra. In fact, I will say in the soft X-ray regime, there are setups that have hit records of 10 millielectron volts. So again, not standard experiments by any means, but this is a field that is evolving. So let's just talk about the types of experiments that these setups actually enable. So I already sort of hinted with the K-beta lines is that these are probes of spin state, and then we have our weak valence to core. Now, what's interesting about these K-beta mainlines is they're actually quite easy experiments to do. And if you look at a low spin shown in red versus an analogous high spin iron complex shown in blue, they have very distinct K-beta mainlines. And these are actually really easy measurements for us to do in-house. They're actually easy measurements to do in a dispersive and time-resolved way. And so these types of measurements have, in recent years, attracted attention from the free electron laser community. But I do want to give a shout out to the fact that this was initially done by Tsutsumi in 1959, the first measurements being done using photographic film, right? But this is not a new method, but it's interestingly a method that largely hasn't been really picked up by the chemistry community. But they are spectra that one can analyze in exactly sort of the term symbols and final state multiplets that we talked about on Monday. So we already did this assignment, but your high spin iron 3, of course, it has this sextet S ground state. And when we actually ionize a 1s electron, that electron can be alpha or beta, giving rise to local septet and quintet S states. It can then relax, and I have final states that are quintet P and septet P. And so in a very simple picture, I should have a final state quintet and septet split by the 3p 3d exchange. As you guys know, there's a full Tanabe-Sagano diagram of low-lying excited states, and so this isn't exactly what we see because we can get a redistribution through symmetry among any of the low-lying allowed excited states, and so the final spectrum looks a little bit closer to this. But these are kind of fun spectra that you can largely understand in a pretty simple pen and paper model. And I won't go through this in the interest of time, but we could do the same thing in the low spin limit. Now, you'll see that I'm sticking to atomic term symbols here because one of the interesting things that one of my former group members showed working together with Mikhail Atanasov, who's the king of ligand field theory. I don't think he's here anymore, but he's just amazing, and he makes me very nervous when he's at my talks, to be honest. So he's gone. Now it's recorded. But anyway, but he actually helped us work through all of this and to sort of understand how these K-beta mainlines can actually change as a function of ligand identity. And what Chris Pollock together with Mikhail were able to show is that we can have high spin iron 3, and these main lines, they actually become sensitive to how covalent the complex is, where actually the splitting decreases because D character is becoming delocalized onto the ligand. And so these actually are measures even of covalency. But again, I always want to be honest and present the caveats, because what we do find is that covalency and oxidation state can actually cancel. And so there are interesting examples where when the D count changes at the same time as covalency, they 100% cancel. And yet, these are complexes that really do vary in oxidation state. They have different Mossbauer, they have different X-ray absorption edges, and it goes back to this, we need multiple methods in order to make these assignments. Okay. What I want to move to now, though, is I've kind of shown you there are clear fingerprints for low spin versus high spin. But one interesting thing to notice is that for different high spin or even different low spin complexes, the main lines aren't changing that much. But if we look at the weak valence to core, these are changing a lot. They look very different for different complexes. They also have very different intensities for high spin versus low spin complexes, where this axis is actually a factor of 4 different for the low spin versus the high spin. So there's a lot of information contained in these weak valence to core features. And this is something that we've been interested through the years in actually understanding. This is something that you will also calculate in ORCA. And this is even more criminally simple than TD-DFT because this is really 1 electron DFT, just looking at the energy difference between the 1 electron cone sham orbitals and taking the dipole allowed intensities. But what we found very early on is that it actually did a really good job of getting correlations between experiment and theory. This happens to be the experimental and theoretical spectra for ferrocene, but it also worked well for the complexes in this study in terms of getting general trends. And the reason that it works well is largely these aren't spectra dominated by any complex multiplet effects or anything particularly sophisticated. They largely are transitions that derive from a small amount of metal p character that is mixed into the ligand p and ligand s orbitals. So this is just the visualization of what gives rise to these spectral features based on a simple 1 electron DFT calculation. Now, why do I actually care about this? Well, it gives me a great way to assign what the ligand is. And that's particularly true for these incredibly weak 2s features. You can see that the valence P levels that are actually involved in bonding, these undergo stronger modulations. But as we already discussed, because of the energetic separation of the 2s orbitals, they're less likely to be involved in bonding. And these energies rather report on the differences in ionization energies going from fluorine to oxygen to nitrogen. And you can see, I mean, this is nearly 10 electron volts that we span in 2s ionization energies. And so it makes it actually quite a sensitive probe, and it's a universal probe. This is true not just at iron, but say I have chromium and I want to know what's happening there, you can also see carbon, nitrogen, oxygen are clearly shifting in the 2s. And so for us, the way we first used this for an enzyme was actually to establish the presence of this central carbide in FeMoco. And this was something that could not be easily done by protein crystallography or by XFs or many of the other methods that were actually tried. And so this was sort of a unique example correlating experiment and theory to show that this was a carbon, because there was a lot of discussion of it being possibly nitrogen or oxygen, which this experiment helped rule out. And it's not just light atoms like carbon, nitrogen, and oxygen that valence emission is sensitive to, but we can even actually detect hydride interactions. And so that's what you're actually seeing here in these iron spectra of these nickel iron models, where you actually have the hydride actually present in the darker spectrum, and that's what gives rise to increased intensity in the experimental data, but also in the calculated data. And we can also then look at it from both perspectives, see that it is clearly interacting with the iron, but it's also clearly interacting with the nickel, and it's present there in both experiment and theory. And so this just gives you an idea of how this works. And then finally, we're also very sensitive to protonation events. And so this is just a related series of dioxo, oxohydroxo, and bis-hydroxo, and just showing how that modulates this region. So the downside is we have an incredibly sensitive region, but unfortunately it's rather hard to measure, but it is possible. And so again, this wouldn't be the first experiment I would do, but it would be an experiment I would try when you really tried all other possibilities and said, okay, I really need to know if that proton is there. And of course, this works so well in a sense because in a simple molecular orbital picture, as we go from an O2 minus to an OH minus, we basically just have this stabilization here, and that's what's actually lowering the energy of that feature. And it does also modulate, I should say. The protonation modulates the shoulder of the 2,5, because, of course, it also is modulating the 2p, but this can become more easily buried. And I've also showed you then, in a sense, we can basically use simple group theory considerations, basically assign the point group of ferrocene, see what our symmetry-adapted linear combinations of ligand orbitals are, and pretty much get a peak that actually corresponds to all of them in that limiting case. I do want to bring up that these intensities are based on metal ligand bond distances. So I showed you that the low spin complexes were actually quite a bit more intense. And that intensity basically comes from the fact that the shorter the metal ligand bond distance is, the more p mixing you can actually get. And so there's basically sort of an exponential dependence on the distance. And I don't have the reference here, but this was an early 2010 JAX paper, where the first author was one of my first undergrads. So she was awesome. Okay. Yeah, so maybe in just the last, I still have a couple minutes. Okay. One of the things we've been interested in, though, I kind of introduced the spectrometer to you as a point spectrometer. And this was the first spectrometer, or at least a drawing of the first spectrometer we built at Chess when I was starting as an assistant professor at Cornell. It really looked like that. We really stole one of these foam containers from a bio lab and stuck it on to have a crude cryostat. That's what it looked like. But we also had the interest that you could use X-ray emission spectroscopy in a dispersive mode. And this is something that's now being widely done, but at the time, this was my little drawing of what we could do, that we could go from a point focus, right, to our detector. We could just move off the Rowland circle, and we would end up with dispersing a range of energies. We just need to replace our point detector with some sort of linear or CCD detector. And so this was something we were interested in doing because we thought that this could be a way to probe reactivity. And so we did this by first asking if we could see something like NN bond activation using valence to core. And so we started with these samples that had chloride. You can see the green is a PDI chloride. And if we add 1 or 2 nitrogens, there was a feature actually growing in here, which we surmised then must be due to coordinated N2. And then we used ORCA to assign this, and what we found is that this feature was due to the 2s sigma star interaction. So we could actually look at and see what that happens. And then we asked the question, well, what happens when that NN bond length actually changes, right? So we kind of just sketched this out old school MO style, basically sort of seeing that as I elongate this bond and eventually cleave it, I expect that the anti-bonding interaction should become lower and lower in energy until eventually it's at the lowest energy point when there's no longer any bonding interaction. And so then we needed molecules to actually test this, and we were fortunate to work with Pat Holland's group, who had a series of complexes that had different degrees of N-N bond activation and even this fully cleaved bis nitride. And what we could see, and these are not the best quality data, these were from that setup we jerry-rigged at Chess in the early days, but I still like the example because it does show how these features actually shift in energy as a function of N-N bond length. And again, we can sort of calculate these with ORCA and get the general trends, and then basically use these in a similar way that you would correlate to N-N stretching frequencies in vibrational spectroscopy. And again, there are many cases where this would be the much harder experiment to do than vibrational spectroscopy, and it's more a question of if there are overlapping features or other chromophores or some reason why you would want to actually do it this way. But just sort of the general message I want to give you is that when we think about X-ray absorption and X-ray emission, we're sort of, in a sense, in a chemist's simple picture, looking at both halves of the same electronic structure picture. And so I sort of encourage you to think about these as complementary halves of sort of the same question. And I alluded to this in my talk yesterday, but the other thing that my group has been very interested in is to combine X-ray absorption and emission together in what is known as resonant X-ray absorption, or RIX, where we have X-ray absorption on one axis and the emission event on another. And so, for instance, you could do a 1s to 3D excitation, follow it the 2p to 1s decay, and here the difference between the ground state and the final state is actually the equivalent of an L-edge. And so there are lots of ways to play games with the selection rules and the experiments. But one of the ways that my group, and I think many other groups, use this most often is to get high energy resolution detected absorption spectroscopy. And so this is basically where, instead of taking that wide electronic window that I talked about that just reduces background scatter, we can take a very narrow window around the 2p, and what we start to see is spectral sharpening. And one of the biggest problems with X-ray absorption spectroscopy is the core hole lifetime broadening, especially for heavier elements. And what happens with these kinds of detection methods is, if you look at the HERF detection, which is shown in blue, you start to get much sharper features. And something like this molybdenum-3 that's completely featureless starts to have features in the HERF detection, in the data, and in the derivatives. And the reason I'm bringing this up is because if we want to make quantitative comparisons to calculation, our data need to have features, right? And so not so satisfying to say it has an edge. Hopefully it has more than one feature. And so these can be helpful in cases where your data suffer from low resolution. Some cool experiments, but again, they remain in this sort of heroic regime, are things like using X-ray emission to get things like spin-selective XFs. And so the demonstration experiment on this was done by Peter Glotzel on Prussian blue, where he actually was able to separate out the low spin iron 2 site and the high spin iron 3 site and get the XFs on those separately. Super cool experiment. Really hard to apply to many things in practice, but nevertheless, if you have very specific questions, there are places where you can think about this. And then finally, another sort of experiment that largely remains a demonstration was early work that we did, starting to think about this as a way to get ligand selective X-ray absorption. So that the idea would be that you sit at a valence to core emission feature that's assigned in this case to a nitride, and you get the XAS just from that feature. Again, lots of challenges in terms of understanding these spectra in terms of theory and experiment, but you're here in Mülheim, and I also just kind of want you to have some idea of the spirit of what drives us, and normally how long experiments are in the making, because this paper's 2014 and we're still working on understanding some data that were collected around that time. Okay, so with that, that's my summary, but rather than read it to you, I'm going to stop here. Thank you for your attention, and I'm happy to answer any questions.